Welcome us to our first lecture on this course. What's the code name? Mat. Bismillah. Mat 8. Is it 812? 801. What's the name? Algebraic structures. Okay. I want to begin this course by giving us a brief history about algebraic structures, like most especially as a group theory. Now, group theory is one of the fundamentals of algebraic structures. We shall see later that from group theory, we are going to evolve into ring theory, field theory, and so on and so forth. Is it clear? But the group theory itself started with the work of Lagrange's in what he called permutations. He was trying to use permutations in solving algebraic equations. That's around 1770, late 18th century. Is it clear? Now all of us know the contributions of Lagrange's, especially in finite groups. The Lagrange's theorem, I'm sure you have heard of it, on the order of finite groups. Is it clear? That's the order of subgroup divides the order of the group, isn't it? That's the Lagrange's theorem. That's the famous Lagrange's theorem for finite groups. Of course, it was debunked later by Silo in cases of P groups, where he found the exception that there are some P groups in which the subgroups, the order of subgroup does not divide those groups. And Silo actually built on it to say that if you want the order of subgroups to always divide the order of the main group, the group order must be a prime number, what you call P groups. So that's what we call Silo P groups. So it's evolved a whole theory there. But the linkage between groups and solvability of linear equations was because scientists or mathematicians were observing structures. You understand? They were trying to observe structures, polytopes, for example, tetrahedron, triangles, heptatopes, hexatopes, all those things. And they were trying to study their symmetries, because the solutions for the system of equations evolving from these structures actually some are finite, some are linear. So the solution set itself, you find out that there is some sort of symmetry in between. And this work was continued up to the time of Galois. Because Galois in 1830 was also the first to develop this theory of Lagrange's into a whole a framework which he called Galois theory. Galois. So after Lagrange's, in what do we say, 1770, who works on what? Permutations. Okay. He was followed by Galois. Around 1830. In fact, around 18, it's even controversial. Some say Galois only lived around 1823. He lived only 20-something years old. He was born around 1811 and he died around this time. So he was only 20-something years when he died. So he lived very short time. But within that time, he developed a whole theory which is called Galois group theory. Just so comprehensive. In fact, he solved this problem was lying. Galois was able to solve an unsolved problem for 300 years, around 350 years. The solvability of quintic equations and other equations evolving from polynomials of higher order, like order 5, order 6, was lying. It was only during the Galois that he was able to solve it into what he called solvable groups. So he used what they call solvable. And according to Galois, a group is solvable if the corresponding polynomial of the solution set of that group can be solved by radicals. And all of us know what radicals are, the system of solutions. So, for quadratic equations, what is x? I have if I give you an example, x squared minus 4, for example, is equal to 0. What do you say? You say x squared is equal to 4, x is equal to plus or minus, which you say what? 2. So you see, in the solution set, you have 2. You either what? They are either on this side or. So if you say this is you are plus 2, you will say this is minus 2. So the origin is lying here. So there is some sort of symmetry. Because the distance here is the same as this. It's like a reflection. So, and so on. If you want of cubic equations, for example, you have 3 roots, isn't it? And so on and so forth. Now, Galois identified this and said that since it means you can permute, it's like flipping around, like a reflection. If I flip around this thing, the whole thing, and so on and so forth. And you can also change the coefficients of these polynomials. You can interchange them, nothing will happen. You can permute them, nothing will happen. So you can play around permutations of these equations. For example, axn a1 a2 xn minus 1 a3 xn minus 2 and so on. These are called coefficients. And the solution sets also. Sometimes if you flip them, it will not change the solution set. Is it clear? And so Galois actually worked so much on this and he identified so I mean, like for example, he discovers that cubic equations is actually isomorphic to S3. And S3, what is S3? It's a group of permutations. Is it clear? Of order 6, of course, of degree 3, but order 6. So he developed all this and he now classified. He said what he said is that from S1, S2, S3, these are all solvable. From S4, S5, they are not solvable. So he developed a classification of this. Just like we say, we know that the quantum equation Ax is this has no solution. This is not solvable in radicals. It has no radical solutions. And from 5, 6, 7, all those ones do not have radical solutions. The polynomials, any polynomial with degree more than 3 has no radical solution. Is it clear? So this work actually continues up to the time of Gauss. Gauss also used finite groups. He works on them, and Cauchy also was the first to define what you call abstract group theory using axioms now. You say a group, a system, a set is a group which satisfies so condition. It has to be this. So those conditions were first established by actually Kelly and Goss. Of course, Goss started them, but they were formalized by Kelly. All of us know the history of Kelly. You know the Kelly table? Kelly. I think 1878. Late 19th century. Okay. And in the 19th century, we will have the work of Burnside and so on, who formalized what you call group representation and so on and so forth. So this is how actually group theory evolved. And it's one of the fundamentals of the other, because you now see the solution set of these polynomials constitute what you call a field, okay? Because you find out they are closed under addition, closed under multiplication, they have embassies, and so on and so forth. So the solution set itself constitute what you call field, okay, field, R, okay? So, and